In this video, we're going to look at biconnectivity. Now you've seen connectivity, so a graph is connected if between any pair of vertices there's at least one path between them. A graph is biconnected if between any pair of vertices there are at least two different paths connecting them. So a biconnected graph is one which doesn't have any separation edges or vertices. So separation vertices, sometimes called articulation points, and separation edges are defined as parts of our graph where if we were to remove them, then we would disconnect our graph. So for example, in this graph, if we were to remove this edge, we would disconnect our graph into one connected component here and another connected component here. So we would have no way without this edge to get from, let's say, PVD to HNL. So a separation edge, if we remove it, we disconnect our graph, or in the case of a separation vertex, such as LGA, DFW, or LAX, removing any one of those separation vertices would again disconnect our graph. So if we remove LGA, we're left with two connected components, which disconnects our graph. Now, separation edges and vertices represent single points of failure in our network. These indicate vulnerabilities of a network. We want to be able to find them in order to either protect against them, maybe we put more of our maintenance budget invested in those points, or to take advantage of them, to disrupt a network. So we want to find in our graph whether or not it's biconnected. So a biconnected graph just means that we have none of these separation edges and no separation vertices. So it's fault tolerant in that sense, that we could remove any one vertex or any one edge, and we would still have, between all of the other pairs of vertices, we would still have a path between them. So our network is kind of fault tolerant in that sense. So this is an example of a biconnected graph. Between any two vertices, there are at least two different paths between them. That way, if we get rid of any one edge or any one vertex, we don't disconnect our graph. There are no separation vertices or edges. So if we have between any two vertices, let's say here's U and here's V, we have not just one path connecting them, but two paths, at least two, maybe more, but at least two paths connecting them. This is the same to say that every pair of vertices belongs to some simple cycle. And in fact, this last definition will be most algorithmically useful for us. So we want to identify the biconnected components of our graph. So this is a maximal biconnected subgraph, meaning that we take some subgraph and we can't add to it any more edges or vertices and still keep that this subgraph is biconnected. Or in the smallest case, this would be a subgraph consisting of only a single separation edge and its end vertices. So for example, here's a graph that has four biconnected components. So we've got one biconnected component here, our second one here, our third one here, and our fourth one here. So each biconnected component has that it is by a maximal biconnected subgraph, or it's just this one separation edge. So notice that any edge belongs to exactly one biconnected component. And if we have a non-separation vertex, for example, SFO is a non-separation vertex, then it belongs to exactly one biconnected component. But if we have a separation vertex, like LAX was a separation vertex, DFW, and LGA, then these belong to two or more biconnected components, exactly. So our goal is to figure out how to find these biconnected components. Because a biconnected graph would be kind of fault tolerant in the sense that we could remove any one vertex or edge, we want to find where these vulnerabilities are in a network. So we want to find what these separation vertices or separation edges are, where they are, and if we can identify biconnected components of our graph, this will exactly give us where those problem points are. So to give a motivating example, let's say we had here a power grid. And we want to figure out what kind of vulnerabilities there are. One of them would be these separation vertices and edges. If any one of them is destroyed or attacked, then it could cause a major power outage, which is not only expensive to fix, but it can have a significant effect on people that are depending on that electricity. Could increase traffic accidents, disrupt communication. It could be fatal for people who are dependent on machines that run on electricity. So we want to find the biconnected components of our graph. We're going to do so by using an equivalence relation to partition the edges of our graph into biconnected components. So an equivalence relation is a relation on a set. So we have here a set, and a relation R is a set of ordered pairs of elements of that set. So for example, I could define a relation on a set of people, on a set of everyone who's watching this video, as let's say person X has the same color shirt as some person Y. So this is an example of a relation. And as it turns out, this is an equivalence relation as well. So an equivalence relation just means that we have a relation that satisfies three properties. It's reflective, symmetric, and transitive. Now this relation is reflexive because any one person has the same color shirt as themselves. This is also symmetric because if person X has the same color shirt as person Y, then it's also true that person Y has the same color shirt as person X. And this relation is transitive because if person X has the same color shirt as person Y and person Y has the same color shirt as person X, as person Z, then this means that person X and Z have the same color shirt as well. Now if we have an equivalence relation, this induces a partition of the elements of our set into equivalence classes. So for example, this equivalence relation would partition the all people who are watching this video into classes based on here's a group, everyone in this group has the same color shirt, everyone in this group has the same color shirt, and so forth. Now we're going to use equivalence classes in order to define biconnected components. But before we work our way up to biconnected components, let me show you how we would do this to define connectivity in a graph. So remember that a graph is connected if between any pair of vertices, let's say V and W, we have some path between them. So there could be multiple vertices and edges along this path. So we can define a relation on the set of vertices as one in which we have a path from V to W. So there is a path from V to W. This is an equivalence relation because it's reflexive. Any vertex has a path to itself. This is symmetric. If I have a path from V to W, then that same path serves as a path from W to V in an undirected graph. And this is transitive because if I've got a path from V to W and another path from W to Y, then I can join those paths to give a path from V to Y as well. And the equivalence classes of this relation partition vertices into connected components of our graph. Now we're going to do the same thing but for biconnectivity, but notice that for this partition we're separating all elements of our set so that they belong to exactly one equivalence class. For biconnected components, if we want to separate everything into biconnected components, we can't use vertices as our set because we know that non-separation vertices will belong to only one biconnected component, but separation vertices can belong to multiple. But edges only belong to one biconnected component. So our equivalence relation will be defined on the set of edges. So we say that two edges are linked if they're either the same or there's a simple cycle containing both of them. Now this relation, this linked relation, is an equivalence relation because it satisfies those three properties. It's reflective because we say if two edges are the same, then they're linked. It's also symmetric because if we have two different edges now, E and F, E is linked with F if there's a simple cycle containing them, which means that F is also linked with E because that same cycle contains them. And this is transitive. So let's say E is linked with F and F is linked with H. Then we can also say that E is linked with H because there's a cycle, in fact this outermost cycle, which contains both the edges E and H. So a link relation is an equivalence relation. And if we were to take, let's say, this graph, and we partition edges based on the equivalence classes defined by this linked relation, we would get 3 equivalence classes. Here we have only the edge A. Here we have the edges B, C, D, E, and F. And here we have the edges G, J, and I. Notice that because of how we defined a linked relation, this is 2 edges belong to the same link relation if there's a simple cycle containing them. Then we've partitioned our edges into, we'll call them link components, but those link components induce biconnected components. So we have here the subgraph induced just by this edge, so this means that the edge and these vertices, this is one biconnected component. All of the vertices and edges induced by these edges, so everything which I've got here is a second biconnected component. And this is our third biconnected component. So if we can find the link components of our graph, then we can use the edges of each link component to induce a biconnected component. So our problem now becomes how to find these link components, because if we can find link components, the edges of that link component form a biconnected component. So we've got, given these biconnected components now, we can find what our separation edges and vertices are, because a separation edge would be the only edge belonging to a single link component, and a separation vertex would be the only vertex that has incident edges in multiple link components. So we'll see how to identify these link components in the next video. If we can find them, we can identify the biconnected components in our graph.